Hello students, welcome back. So at this junction at the chapter of current electricity, we will try to study about electromotive force EMF, that is the power source which drives current in the electric circuit. And we will also study about a very important physical quantity, that is potential difference. And moving further down this path, we will study about internal resistance of the cell and also the different combination of cells available, that is series and parallel combination. So let's start.
Now we'll try to shift our focus to EMF and potential difference, and also the difference, or let's say the minor differences between EMF and potential difference, and what is internal resistance, and what are the different possible combinations of cell. So let's start off with EMF and potential difference. So EMF is basically electromotive force, and it is the maximum potential difference between two electrodes of the cell when no current is drawn from the cell. That is, let's say the circuit is open and we have connected a cell. So that is EMF. Potential difference is the drop in the potential in the circuit apart from the power source. That is the EMF. So there is a slight difference between electromotive force, that is EMF, and the potential difference. So to be more clear on this particular front, that is what are the differences between EMF and potential difference, so we should jot down the different points of it, points of difference. So here's a table which we made regarding the differences of EMF and potential difference. So the first one goes the same as the definition, that is the maximum potential difference between the two electrodes of the cell when no current is drawn from the cell, that is when the circuit is open, as I said earlier. And the other half of the difference, that is the potential difference. Potential difference is the difference of potentials between any 2 points in a closed circuit. That's the potential difference for you. The second point is it's independent to the resistance of the circuit, as it's written earlier that irrespective of resistance, that is whether the circuit is open or closed, electromotive force in a nutshell is the drive, or let's say the ability or potential of a cell to drive the current through a circuit. So whether the circuit is closed or open, it doesn't depend upon the circuit. So that's what it's written, that it's independent of the resistance of the circuit. The other point of difference, it is proportional to the resistance between two given points. Obviously, when the current is flowing in the circuit, if we take up any 2 points, the potential difference across those 2 points definitely depends upon the resistance between these 2 points. So the dependence of potential difference on resistance does make sense. The last point of difference is it is greater than the potential difference between any 2 points in a circuit. Obviously, because EMF, or let's say EMF of a cell, is the ultimate driving force, and that potential gets dropped as the current moves in the circuit and ends up back in the cell. So any potential drop in the circuit has to be less than the electromotive force. The last point of difference is potential difference is greater than EMF only and only if the cell is being charged. That is, the current now is driven in opposite direction. That is, current which usually moves from positive electrode in the circuit to the negative electrode on the other half of the circuit is now moving from negative electrode to the positive electrode through the circuit. So it's only then that the potential difference can be greater than the EMF of the cell. So here we have just listed down a few of the points of differences between EMF and potential difference. So we now move on to internal resistance of the cell. So internal resistance of a cell is basically the opposition which is offered by the electrolyte of the cell to the flow of electric current through it. So it's kind of similar to the resistance which we studied regarding the conductors. In solids, when electrons flow inside the conductor, they encounter collisions with other electrons and also the atoms. And this was being perceived by Simon Ohm as a resistance. Similarly, in case of electroids, when the ions try to move across the electrolyte, they encounter collisions with other ions. That is, let's say a negative ion is moving from one point to another point. So the negative ion collides with other negative ion or the other positive ion, and that is the resistance in itself. So hence in electrolyte, again the collision plays the important role. So in solids, it was electron-electron collision or electron-atom collision. In electrolyte, it's basically ion-ion collision. So now, the factors which affects the internal resistance of the cell. The first one, the larger the separation between the electrodes of the cell, more the length of the electrode through which the current has to flow, and consequently a higher value of internal resistance. It's the similar context where the resistance is proportional to the length. It's one and the same thing. So as the length between the two electrodes is greater, now the ions need to travel a great amount of distance. So larger the distance, larger will be the number of collisions, hence larger is the resistance. And this resistance is actually internal in nature because electrolyte is an internal part of a cell. So moving on to the second factor which affects the internal resistance of the cell. Greater the conductivity of electrolyte, lesser is the internal resistance of the cell. That is, internal resistance depends upon the nature of electrolyte. Obviously, if the electrolyte offers less amount of collisions or facilitates good movement of ions, then definitely the resistance will be low. The last point of the factor which affects internal resistance is internal resistance of cell is inversely proportional to the common area of electrodes dipping in the electrolyte. This is a similar concept where the resistance is inversely proportional to the area, the cross-section area. So in electrolyte also, the common area between the electrolytes dipping acts like a cross-section area because the ions will be primarily directed between those areas. So hence these are the factors which affects the internal resistance of a cell. Now we want to calculate what is the internal resistance, or let's say what is the current flowing in a circuit where internal resistance needs to be considered. So here I have a cell with an internal resistance R and electromotive force of E, and it's been connected to a resistance of R which drives the current I. Now I want to calculate what is the value of current I. So E here is the electromotive force, V here is a potential drop across these points, that is across the external resistance R. Small v here is a drop across the internal resistance R. So this is the small v and this is the capital V. So we can definitely write E, that is electromotive force, to be IR, current in the circuit, multiplied by the external resistance R, that is, this gives me the value of V. I into small r gives me the value of small v. So E is equal to I times R plus capital R. So finally we get the value of current in the circuit to be E divided by the net resistance, that is external resistance plus internal resistance. So this relation is basically circuit equation. Why is this called a circuit equation? Because it relates different parameters of circuit to current. This is EMF, this is external resistance, this is internal resistance. So hence this fancy term of circuit equation. Now we'll try to calculate the value of internal resistance of the cell. So again the same setup, that is I have a cell of EMF E with the internal resistance R, the potential drop across it is small v, there is an external resistor R, the potential drop across that external resistance is V, the current is driven in this direction. Now my intention is to find out the internal resistance, that is the small r. So what we did is, we have started off with the same set of equation, that is E is equal to capital V, potential drop across the external resistance, plus small v, potential drop across the internal resistance, and substitute the values of different expressions. So small v is equal to EMF, that is E minus capital V. we know that small v is equal to I, that is the current in the circuit, times the internal resistance. Now we are dividing it by IR, that is the capital V, or the potential drop across the external resistance. So IR is equal to, so this expression IR, we are dividing it by this I capital R. So we will end up getting this expression, that is internal resistance is equal to EMF divided by the potential drop across the external resistance minus 1 times the external resistance. So we end up getting the value of internal resistance. So we know about the EMF of the cell, that is what's being written on the cell. V is the potential difference which we can calculate by introducing any meter or sort, that is voltmeter or galvanometer will do the work. We also know about the external resistance, hence we can easily evaluate what is an internal resistance in the circuit. So now we'll try out the different combination of cells. That is, first we will try out the series combination of cells. So in series combination kinds of looks like this. So I have a cell of EMF E and internal resistance R, and they are connected in series with an external resistance of R, and current I is being driven in the circuit. We know that EMF of the battery is the sum of the individual sums. Obviously these potentials will tend to add up, and the current in each cell is same and is identical with the current in entire arrangement. So as this is a continuous circuit, so current in each branch and in each cell is one and the same. Now total internal resistance of the battery is sum of the individual internal resistance. Exactly, if the resistance are connected in series, so these resistance are connected in series. That is, 3 internal resistance over here are also connected in series with the external resistance. So now we'll just evaluate the different things which we know of. That is, the total EMF of battery will be NE, that is N being the number of identical cells. Total internal resistance of the battery will be NR, and again being the number of identical cells, and R being the internal resistance of each of these cells. Total resistance of the circuit will be this much, that is the net internal resistance plus the external resistance. And the current in the circuit will be obviously given by the total EMF of the battery, that is this one, total EMF of the battery divided by the total resistance. So if we apply some special conditions to it, that is, if let's say external resistance is much less than internal resistance, then we get current to be E by R. That is simple. This looks like this. And there is an EMF of E, and this is the internal resistance R, and this is a cell of EMF E. So this gives us an idea that there is a cell which has been short circuited, that its two ends are simply connected. Now in second case, that is net internal resistance is much less than external resistance, then the current in the circuit becomes this. That is, I is equal to N times E by R. Now the conclusion which we can make out regarding the cells in series combination is, when internal resistance is negligible in comparison to external resistance, then the cells are connected in series to get the maximum current. So obviously you can make out with the two conditions which we have discussed that this conclusions is pretty evident. So now we'll move on to cells in parallel combination. So cells in parallel combination, so cells are said to be connected in parallel when they are joined positive to positive and negative to negative, such that the current is divided between the cells. So it's pretty evident. So based on the above stated setup, we can find out that the total EMF of the battery still remains to be the same, that is E. Total internal resistance of the battery, obviously it falls on, because now the internal resistance of the cell now are connected in parallel. So the net internal resistance comes out to be R divided by N, N being the number of identical cells. So the total resistance of the circuit comes out to be R divided by N plus the external resistance.
So students, in this part we studied what is EMF, that is electromotive force, and what is potential difference, and also the difference between EMF and potential difference. We also studied about internal resistance and how does it affects the output current in the circuit, and we concluded off with series and parallel combination of cells. So in next part we will move on to how to solve the complex circuits in current electricity. So stay tuned.